Are you John? Are you Silva? So I have one more thing to get set up in my hardware set up here. But in the meantime, what I'd like to do is a quick exercise, just to make sure we have some vague, fleeting memory of what we did last week. It's been a week since we did flow. That's a week too long in my book. So what we're going to do is pair up into groups. People sitting nearby, just pair up with someone nearby you. Two, preferably, or one. I would like you to take this network. I would like you to run, well, I want to find the max flow. You could presumably find it by inspection, but that's not what I want you to do. What I want you to do is run the Ford-Fulkerson algorithm. And you will find, of course, that as you run it, there are choices you have to make, questions, and the whole point of this exercise is to sort of, get you comfortable with how the algorithm works. And we talked about the algorithm last time. Hopefully you remember it. Hopefully you have notes or something that tells you how it works. So, I will give you about till 55. So it's about 47 right now. I'll give you about 55. To work through this. And again, I don't want the answer so much as I want you to work through the algorithm to get the answer.
You have to turn it just as
oh, yeah, I'm here.
yeah. But you have to turn it against one.
For those who came in late, the first exercise is to run the Ford-Fulkerson max flow algorithm onto this graph and get me the answer. Again, the goal is not to get the answer so much as do the process itself. And I'm hoping that in the process of doing this, you'll have questions, you'll have clarifications, and I'll start walking on the route to see what's going on. Pair up in groups 2. In the worst case, 3 groups. 2 groups is better. Talk about this. If you have a question, you can raise your hand.
Leaving the field.
questions so far? The trick is to treat the residual graph as if it were your tree graph. All the arrows are as they were on your tree graph. Just follow start with the right direction. No, find a path from start to finish. Any path. The core focus is find any path from start to finish. Find the edge with the smallest capacity along that path. And then what does that mean? If you have a path, it's a directed path. So you're pushing flow along the direction of the edges. You don't have to worry about what you did on that edge of here. That's the whole point. You can forget everything. The whole genius of the residual graph is it allows you to forget what you did. Did I push through all this much? You don't care. It doesn't at all.
It's not hard.
You just have to treat like a new graph.
Yeah, and then if you wanted to prove that, you could create, I mean, your max flow is minimum right?
Hey, do you all want a bit more time or are you mostly done?
Can you put it back on?
Oh, what's happening here? Oh, sorry.
Thank you.
Some of the people are still working, so maybe another 3 more minutes.
Just wasn't paying attention. When I was here. Yeah, I thought it was. Yeah, I was thinking. I think it was talking about the paper. I have a question. I think I led all of the students astray when I answered their question because they were asking about October 8th. That's the deadline for the first submission, right? And then they have between then and the end of the semester to do their second one. Sorry? Oh, the end of the semester one? I'm not sure. I'm guessing last day of class.
Okay, I think it's about time. Okay, so what's the max flow? The number. I hear some votes for 5. Are there any votes for any other number? 6. Okay, there's some votes for 6. Good. Any other numbers? 7. Do I hear 7? 7. Not going to hear it. Okay, it's good. We have 2 answers. We have a 5 and we have a 6. I personally have no clue what the answer is. I didn't do it. could one of the, let's see. So anyone who said 6, who said 6?
I said 6.
Good. Tell me what the flow assignment is to get you 6.
Boy.
No, just tell me what the flow on the edges are, or just give me, the edges. Yeah, I'm gonna give you 6 here. So I assume you're gonna saturate you have to saturate the flow out of the source.
Right.
Okay.
Actually, now I'm looking at it. I actually got 5.
It's a 6 that looks like a 5. Okay, good.
Actually,
Oh no, wait.
yeah, I got 5.
I'll give you 30 seconds to change your mind.
I got 5. I
Five.
just counted.
So we have no contention. So 5 must be the right answer. No, of course not. So okay, someone who said 5. Anyone want to? Someone who said 5? Yeah, go ahead.
I did 3 along the top,
So 3 from S to A,
3 from S to A, and then I had 2 from S to B,
2 from S to B.
and then I
Okay.
had 2 from B to C,
Yes.
and then I had 1 from C to A,
Okay.
as I also put, and then I put 4 from A to D,
Yes.
and 4 from D to T,
Okay.
and then 1 from C to E,
E and then E to
and
T.
T to T.
This is definitely a valid flow. It satisfies all the capacity constraints. Do we know if it's max? So the argument, of course, is I couldn't do any better, is one argument. Go, so can we say what the max, can the max be 7, by the way?
Nope,
Why could the max not be 7?
we don't have 7.
So in particular, sorry, we don't have any link.
T to D is the only link.
That's not an argument.
The source only provides 6.
The source can only put out 6. No matter what you do, the source is only going to put out 6 flow. So there's no way to get more than 6. So at least we know it's okay. It's not more than 6. And we have an answer that's 5. Can we be sure that 5 is the right answer? How would we be sure? We've actually talked about this. There's a way to be sure that 5 is the right answer. How would you be sure of that? Yes?
If you do the cut afterwards, you end up with S. The cut goes from SB is in one set.
Hold that thought. Well, tell me what the cut is here.
The cut would be SB in one set and then the rest in the other set.
Okay, so the claim is that 5 is optimal because I can produce a cut whose cut value is only 5. A cut is a set of nodes that contains the source, which is very important. So the proposed cut you're saying is S and B. What is the total capacity of edges coming out of S and B? There's an edge from S to A. There's an edge from B to C. There are no other edges going out of the cut. There are edges coming in. Right? And that is 5. If you remember the flow assignment that Nick mentioned, it has those 2 edges saturated. In fact, it is actually pushing out 3 along that edge and 2 along the other edge. If you remember the proof that max flow is equal to min cut, it says this exactly will happen. That there will be a cut and you will push all the flow you can out of this cut. And these 2 are going to be equal. And that's why you're going to get a proof that this is optimal. Because no matter what flow you came up with, you have to deal with the fact that out of S and B you can only push 5. It doesn't matter what else you do. So we were feeling happy about 5 because we knew 6 was the largest number. But we couldn't have been sure till we found the cut SB. But how do I find the cut SB? Is it, inspiration or what? Is there a systematic way to find the cut SB?
Probably.
Sorry?
Probably.
Probably. Oh, no. That's not good enough. We talked about this as well. How would you, if you remember the proof of the min-cut max flow theorem, I said, okay, in order to prove that Ford-Fulkerson gives me the correct answer, I'm going to give you a cut that matches the flow value that Ford-Fulkerson gives. And I'm going to use the Ford-Fulkerson result, the flow I get, to produce such a cut. So in fact, the proof had an argument for how you're going to do this. Anyone remember this? So I don't have to be inspired, I can just construct it, yes.
So you start from the source and you travel along those edges that have non-zero remaining weights for the nodes that you can visit from there, and those constitute the cut, if that makes sense.
Yes, it does make sense. And in fact, that is the correct answer. That if you take the Ford-Fulkerson flow result and you say, okay, after I push all the flow and add this residual graph, what can I now reach from the source? We know we can't reach the destination because Ford Fulkerson stopped. If you could reach the destination, you'd have another flow path. So you have some set of nodes, and then we showed that the cut value coming out of this would in fact be the flow value. Here, if you recall, we said we're going to push flow of 3 through A and 2 through B. So let's just think about that for now first. If I push a flow of 3 through A in the residual graph, can I get from S to A? Not sure. If I push a flow of 3 on S through A, I'm going to have one edge. I'm going to have an edge going out of capacity 0 because I've saturated, an edge coming back of capacity 3. Right? If I push a flow of 2 from S to B, I get a capacity going out of 1 and capacity going back of 2. Okay. So from S already, I know I can't reach A after I've done the flow augmentation all the way to the end. I can reach B. Okay. Can I reach from B anywhere else? No, because if you recall, we pushed 2 units of flow from B. So there's no way to get to C now. In the residual graph, there's a back edge of capacity 2, but there's no forward edge. And there's no other way. So if you took the flow result that we talked about, and you said, okay, what can I now reach from S? You can only reach B. And so automatically you know that is the cut that you want. And that cut will have the right flow value. Yes?
If B to C was 3,
Yes.
then SBC would have given me the min cut, not SB, right?
If SBC was 3, would the flow value still, max flow value still be 5?
Yes.
I hear some notes here.
Because if I take, I can use your own theorem, right? If I take a cut which is SBC,
Okay,
the
yeah.
output is 3.
1, 3 from A, yeah.
Okay, and from C I have 1 going out, which is 2.
Okay, good argument. So here's an interesting argument. Suppose we change the capacity on BC to 3. Would the max flow value change? And his argument is no, because now this new cut, SBC, has 1 edge going out of capacity 3 from S to A, and 1 edge going out from C of capacity 2. Still 5. The other edge going out from C goes to A. But that also goes to A. That's 6.
Oh, yeah, sorry.
So now we can no longer be sure that 5 will remain our max flow value. It might be, but we have near different argument. Right? Yeah.
But my question is, how can you make an argument saying then in some cuts I get more values than 5, right? Or I'm just finding a
Remember, min cut is max flow. Think of it this way again. Think of it in terms of choke points. It doesn't matter how many choke points there are. The smallest choke point is going to control everything. So you don't need to care about other bigger choke points. It's the smallest one. That's a problem for you. The most flow you can push is through the smallest choke point. Yes.
I think if B to C had a capacity of 3, your cut would actually include E with S. Yeah. Because you'd still be able to get to E because you're only pushing 1 from C to D.
The claim now is that, you're saying your cut would have to include E?
Yeah. Yes. So you'd still have, would still have max.
So what would the cut, suppose my cut now is SBCE. Tell me what the cut value is. So my cut is SBCE. How much capacity is coming out of this new cut?
No, 6. Because C is also pushing 3A.
So S is pushing 3 through A, C is pushing 1 to A, that's 4, E is pushing 1 to T, that's 5, and that's it. So now we know that even if you increase the capacity of B by 1, BC by 1 to 3, it won't change the flow because there is a cut now still that has capacity only 5. And maybe the actual flow changes, or it could change. Increasing capacity will not change a valid flow, of course. But nevertheless, you will not be able to increase the overall flow. Any questions? All make sense? You feel like you understand how Ford Fulkerson works now? So you may have noticed a certain amount of arbitrariness in how Ford Fulkerson works. When you're running it, did you have to think about, okay, which path should I choose next? Were you thinking about that? How do you decide which path? So at this point, there are many ways I can get from S to T. How do you decide which way to go? Did you have any particular system you were using, or you just chose whatever? Yes? Is there a half hand in the back there? No? Okay.
Just use the largest flow coming out of S.
Just use okay, that's reasonable, yeah. The point is that there is no reason to be particular. Any path will work. You don't have to have a rule to make Ford Fulkerson work correctly in terms of finding the max flow. We are going to see today that the particular choice of path you pick will change the running time a lot. But as far as finding the max flow goes, it doesn't matter which path you pick, because the proof only assumes that there is always, that you stop when no path remains. The order in which you pick them does not matter. And that's very important. Did you have a question, Matthew? Okay. All right, yes.
You didn't prove that we have a unique solution.
Do I care? Should I have a unique solution? Do I want a unique solution? Does it matter?
If you're having multiple algorithms, then trying to get one depends on which unique.
So the question, okay, so maybe I should clarify. The question is about unique solutions means there is exactly one solution to the problem. I have made no claims about whether there's exactly one solution to the problem. All I said is there is a solution. In fact, maybe there are probably multiple ways of assigning flow to get flow of file, and they're all good. Yeah. In fact, there will always be an infinity of correct solutions. The problem is there's more than one. Because any convex combination of two solutions will be a valid solution. If you allow fractional values, for example. So there's a continuum of solutions. There may be a discrete number of integer solutions, but there's always a continuum of solutions. It's a linear program. So you know. But there could be. If there's more than one, there could be many. If there's exactly one, then yes, it's only one. Okay. Before I move on, I was told, I was instructed to make an announcement. This is as part of the tending and care of TAs sort of program that we have here in the class. Don't harass the TAs about partial credit for extensions. As I mentioned, syllabus, there are none. If you submitted late, you submitted late. If you didn't submit late, you get the points for it. We're not going to do partial credit. The same thing for the homeworks. And the problem at the particular question level, the granularity will be 0 or 1 for each particular problem. There will sum whatever the points are or not. And that's why we have the resubmission process, so you can make sure you don't keep on losing. So I just want to remind you of that policy. Yes?
So like 25-point questions will eventually just be like 1 or 0?
Yes.
Okay.
Which is why it's important to make sure we go back and forth with these. Yeah. What else? There was another announcement. Oh, yes. So I also posted a sample question, a sample two answers, one for recurrence and one for one of the other algorithm questions. This is a good template, both in terms of at a low level how you use the LaTeX to do this, to put a solution thing, and also at a higher level how to express yourself and how to write down the answer. Okay. I don't think that the answer has to be at that level of detail, but I want to provide a model for what is ideal, right? And so you have to. That's something you should aspire to. That level of precision and that level of detail. Okay. All right. Let's move on. So let me get this into full screen mode. Okay. The problem with Ford Fulkerson, as I mentioned, is that they can take a long time to find the right answer. I threw out a little note yesterday about last time about why it's not going to polynomial time. We'll get to that. Suppose you have a network that looks like this. Okay, I didn't mark source and sink. Source is on the left side, sink is on the right side. What is the max flow in this curve? X is some number.
2x.
2x. Like, what's the problem? Take 2 steps. One flow that way, one flow that way. You're done. Right? But remember what I said about Ford Fulkerson. It can take any path it wants. It doesn't have to take the smart path. Doesn't even know what a smart path means. So here's what could happen. Suppose it takes the path going down. Well, let's say it takes the path going up, then down, then across. How much flow can it contribute? 1. So you increase the flow by 1. Okay. Now it goes down. It goes back up because now there's a reverse edge. Because I did a residual graph. And comes back down again. Now I have
2.
Now it goes up, comes down, and goes across. I have 3. Goes down, goes up, and comes across. I have 4. How many iterations will it take to get to the optimal solution?
Way too many.
2x. It'll take 2x iterations to get to the optimal solution, which is the flow value. And that's what I said, right? That you can upper bound the running time of Ford Fulkerson by the number of edges times the total flow coming out of the source. And in fact, up to a constant, that's exactly what's going to happen. You're going to spend 2x, which is the total flow coming out of the source, total capacity of the source, iterations. In each iterations, you touch 3 of the 5 edges, which is terrible. It's not just terrible because it's dumb, it's terrible because this is not polynomial time in the input size. And I know there was a lot of puzzled faces when I said this last time. So I'm going to say it again now. This is not polynomial time in the input size. And I think it's a good thing to think about why. This is not a polynomial time, this is an exponential time algorithm.
What is input when we say we have to work?
The input is whatever you need to run the problem. So the inputs consists of the graph and all the weights on all the edges, all the capacities on all the edges, right? Because you need to give the inputs. So why is this exponential time? Or why is this not polynomial time in the input size?
Is this one of those captures where it's pseudo polynomial?
I could say yes if we all knew what pseudo polynomial was, but since we don't all know what it is, I can't really answer that question. So maybe if you can answer the question without using terms.
So is it one of those where it depends on how you represent the input?
Everything always depends on how you represent the input. But yes, that is, you're getting close.
Okay. So it's like, if you think of like the I can't remember the exact complexity, but if you think of the capacity coming out of the source as a binary number or something like that.
Yes.
Doubling the size of, yeah, so that's kind of where I'm going.
That's where you're very close, yes. Yeah.
Because when you are finding out the flow, you are talking about the power sets of the edges.
Why am I talking power sets of the edges?
So consider the set of edges.
Yeah.
And the
But there are only 5 edges in this graph.
yeah, and the flow that you are constructing, those are the solution. The possible solutions are the power sets of that.
No, there are only paths from source to sink. I'm not looking at all possible sources. It's a linear, sorry, what's it?
It's a combination. It's a linear combination of the.
But not all of them. Only of interesting paths from source. I have no way of reasoning about the number of paths from source to sink. And I'm giving you this very simple graph here, right? And this is not a graph where these issues should be of importance here. Yes?
So if we take for this graph, for example, and the worst case, I'm having one unit and it's choosing from the paths it is going.
Yeah.
So in some sense, there are like, in this case, we have 3 paths it can choose.
Sure.
So it's every time, every unit has to choose 3 paths, and every time it can choose differently.
No, it could, but I'm not exploring all possible paths. I'm using an actual running. I gave you the algorithm. Do this, do that, do this, do that. I'm not telling you what it could do. I'm telling you what it actually is doing, and I'm saying that itself is not polynomial pattern. I'm not saying that this could be a problem. I'm saying it is a problem for the actual run of this algorithm. Yeah. Why? I mean, Charlie was very close, but 95% of the way there. So, the point is the following. If you have to write down the input to this problem, you need a graph. So you have vertices and edges, and you need weights on all the edges, capacities, right? When we write down numbers, we use, if I write down the number, I don't know, 63. How many bits do I need to write this down? I mean, if I didn't have board alignment issues, I could write down 6 bits. Right? In general, I might use some particular integer type, and I might use a 32-bit integer to write it down, whatever. But I don't need so many bits to write down this number. I definitely don't need 63 bits to write down this number. Right? In other words, to write out an actual number, like 20 or 100 or 200, the number of bits I need to write it down, that I always use to write it down, is the log of that number. It's not the number itself. So when I have to look at the total input size of this problem, I have these 5 nodes and I have interconnections between them. So there are, there are n nodes, n edges. I need log n bits to describe the ID of a particular node. So I have n nodes, each has log n bits. I have n edges, each has 2 log n bits. So it's 2m log n. So you have n log n plus 2m log n plus all the bits required to write down the capacities. But the total number of bits required to write down the capacities is basically the sum of the log of the values. So it will be log of x plus log of x plus log of x plus log of x plus 1. 4 log x. So the input size is, n plus m, in this case it's 5 plus 4 log x. That's my input size. But my running time is a function of x, which is exponential in log x. And that's why this algorithm is actually running polynomial time in the input size. And if you think I'm sort of splitting hairs here, it would not be a stretch to say that all cryptography rests on this basic fact. If I have to factor a number, it's not hard to write on an algorithm that looks like polynomial time in the value of the number. The reason why a 256-bit key is so much better than a 128-bit key is because the actual values you're dealing with are exponential in the size of the input. But you can write them on compact. And if you couldn't do that, if you always wrote down everything as length of the value itself, then all cryptography would just collapse. And all NPR problems would become, many of them would become, not all, many of them would become easy. So this is a distinction that again is, you may not appreciate just yet, but it is an important distinction. And it's important, A, because that means this algorithm is very inefficient, we need to fix it. But it also means that, and we'll come across this later on, that the size of the input is not n. It is whatever the size of the input happens to be for your problem. If you're trying to factor a number, n, the size of the input is not n, it's log n. If you want a polynomial time algorithm to factor a number, it has to be polynomial in log n, which is good because it's very easy to factor a number in times square root n or something. You just find all those prime factors. That's not hard to do. But it's very hard to do it in time polynomial in the log of it, which is what matters. So that's one issue with the Ford-Fulkerson algorithm. It is very inefficient because of this issue, because of its arbitrariness and the way it chooses edges, that can take a very long time. There's another issue that's even more annoying that relates to the actual numbers themselves. So remember we argued that the Ford-Fulkerson works and always converges because you have integer values and you always make progress. And so you could say, well, I can only prove it converges if I have integer values. Maybe it still works if I don't have integer values, but I can't really argue about how long it takes. So it works, but I can't prove it. And that's actually not true. And there's a very clever example that was developed to show this, that if your capacities are not integers, then not only will Ford-Fulkerson take forever to finish, it will take forever to finish and give you the wrong answer. It won't give you the right answer. So I mean, you could hope that it takes infinitely long and still gets you the right answer. Even that way. It will converge to an answer that's way off whack from what the right answer should be. Because again of how it chooses things. And this graph is kind of very weird and interesting. So let's say this is my network. The source is at the top, the sink is at the bottom. Think of some very large number x which labels the capacities of some of these edges. And think of some small number phi which labels the capacity of that one edge over there. Okay? And we're going to choose phi so that this relationship holds. This is the Fibonacci type thing. So phi is going to be a small number here. You can solve for phi. All we need is this property to work. And it turns out if you run Ford-Fulkerson on this graph and run it to infinity, it will give you a flow value of 7. Or some numbers just like this inside. What is the flow, max flow value?
2x plus 1?
So I can do 2 big x flows coming out, right? And then 1 unit flow in the middle. So I can get 2x plus 1. Think of x being 100. I can get 201 flow. Ford-Fulkerson will give me 7. I could make x 1,000. Ford-Fulkerson will still give me 7. The argument is a little intricate, and it's in the notes, and it's very interesting. Basically, what you do is to prove this, you construct a sequence of updates, which are all valid Ford-Fulkerson updates. They all meet you from start to finish. And you use this fact very carefully. So in particular, what's going to happen is you're going to start with this. I'm going to do this flow augmentation here. So that's going to be 1 unit of flow. And I'm going to keep track of what the capacities are on all these edges right now. Okay, this 1, 1, 1. So I'm going to write up there 1, 1 phi. So when I do this flow, it's going to look like this now, right? I have 1 unit of flow, and now that edge has capacity 0, because I pushed 1 unit through it, so it's going backwards. And now the next unit of flow I'm going to pick is going to be a flow value, which goes like this. Its total capacity is going to be, let's see, phi is a number which is less than 1. So its total flow capacity is going to be phi. Okay? It's going to push through this way. So what's going to happen is that this is going to change, and now the new flow value is going to look like this. This is going to be 0, this is going to be 1 minus phi, and this is going to go back to being 1 again. Or it's going to go back to being phi again. So this is a relationship here. Sorry? And then you do it again, the third part, and again you update the flow values. You do another one like this, and get the flow values. And you keep doing this, again using the fact of this relationship to simplify things. And at some point you stop, because I started repeating myself. Notice that I had layer 0, which had a flow value, a capacity of 1, 0, and phi on these three edges. If you go up these 4 steps, I now have the same configuration, but everything is multiplied by phi squared. So instead of 1, 0 phi, I have phi squared 0 phi cubed. So now you can repeat the whole process over again. And at the end, you'll get something that looks like this. And phi is less than 1, so this will run for an infinite amount of time in order to get you to these capacities to drive to 0, where you can't, everything is completely blocked and you can't do anything. And at that point, you can sum up all these values to say, okay, what is the total flow? And you can, the calculation, you can do something like this, and you get something like this. The number is a little less than 7. And again, this is a valid forward focus and implementation. As I said, the true flow value here is 2x plus 1. So not only is forward focus bad that it could take too long, it's bad that it could take too long and give you the wrong answer if your capacities are not integers. So, V1.
But here, is it because of float point error or is it because of...
Because of what?
Is it because of float point error or is it because...
No,
the series are...
it's not floating point error. It's that the algorithm itself is intrinsically just not going to... The guarantees we proved work only if it's integer.
But you
Or rational.
But there's an approximation when you said 1 minus p0.
No. I'm defining phi such that this is exactly true.
And solve for that.
Yeah, it's all for sure. Yes.
So, like, is there, I don't know what this is, but what about the argument where you say, I have all these decimal numbers such that they don't become integers?
You can do that as a rationals. Phi is not rational here. Phi is an irrational number. It's going to be some square root of something, I forget what. There's going to be a square root of 5 somewhere in there. So it's irrational. You can't do that here. With rationals you can. You normalize everything in integer. But then remember, now your numbers are getting big. Right? And we always said 4% is bad if the capacities are big.
That is still correct.
That is still correct. So we've gone from bad and incorrect to bad but correct. What we'd like to do is get to good and correct. Right? And that's a plan for the rest of the lecture today. Okay? Alright. So I think I'm going to switch over now to some non-slide. Oops, what did I just do here? I think, yeah, this is it. So let me just switch over to a different mode. What I'm going to do is scribble pad. Yeah.
So we were wondering, I mean, so this would be like the worst case scenario for the algorithm. So would it be possible for the algorithms to choose the correct paths that produce the optimal?
Yes.
Well, okay.
We're going to talk about that right now.
What's that?
We're going to talk about that right now.
Okay.
For some reason I need this. So magically make everything work. Okay. Easier to draw. Okay, so let's see. Okay. So as we've been observing, we would like a flow algorithm that runs a little bit more efficiently to be nice and grandful all the time. And thankfully, there are ways of doing this. There are basically 2 different approaches to doing this. And they both go along things that you've all been alluding to. Namely, have a better way of choosing an augmenting points. Don't just choose it arbitrarily. Be a little smart. And we're going to be smart in 2 ways. Hopefully I can get to both of them. One we'll call, let's see, fat pipes and short pipes. So let's start with the fat pipes argument. So remember that the basic Ford-Fulkerson structure is find an augmenting path from S to T, augment along this path, repeat. Keep doing this till you can't do any more. We are not changing that structure. We are merely saying find a good augmenting path from S to T. That's all. And the definition of the word good is what we'll just find in the algorithm. Okay? So the fat pipes argument basically says So I think one of you had already mentioned this, that when you try to find an augmenting path from source to sink, try to find the path along which you can push the most flow. Okay? For now, let's not worry about how we find such a path. It's actually not hard to find such a path. So we'll skip that for a second. What I want to focus on is what happens if you do that. Okay? How that changes the running time. Because the game we want to play here is reducing the number of iterations of the algorithm to something that's reasonable, something that's prolonged. Alright. So again, let's pretend we know how to find this largest augmenting path. We call it the bottleneck path. So the bottleneck edge is the largest possible. So the minimum capacity edge along the path is as large as possible. And we keep doing this. So I'm going to show you now how to show that this actually will converge in reasonable amount of time. Alright. So let's say that here's what we're going to do. Let's say we augment. So let's say we are running the Ford Fulkerson algorithm. At the first step, right, we find, so at step 1, we find a path with capacity, with bottleneck capacity, so the minimum capacity, C. Okay? What we'd like to say is that somehow, when we find a path that has large capacity to push on, this makes good progress towards getting the max flow. Right? So if you think of the max flow as some big number, right? And every step of the way we're carving off a little piece of it to get to the max flow. The problem with Ford Fulkerson is just carving by little pieces. And some want to argue that when you do this with this kind of greedy-ish approach, where you take the largest flow possible, we carve off large chunks. And so we quickly get to the end. Okay, that's the plan. So how do you reason about that? So the reasoning is going to go by saying that essentially we're going to be able to show that this is a reasonable fraction of the total flow, of the max flow, whatever it happens to be. Okay, so let's see how we argue this point. Okay. So let's say that this path, so let's compute a cut. Let's compute the set up all of V such that there's a path from S to V using edges only of okay. So I found this path with capacity C, which is the best path possible, and now I construct a set of vertices. So first of all, I claim this is a cut set. In other words, it contains S and it does not contain E. Why is that? So I've said two things. The bottleneck path, the path that has the largest flow possible on it from S to T, has capacity C. And now I'm going to look at all vertices reachable from S using edges of capacity more than C. And I claim this set is a cut set. That it contains S but doesn't contain T. Well, it trivially contains S. Why doesn't it contain T? Why can this set not contain T? Based on what I just said.
Because you already argued like the bottleneck that you have is of the capacity C from S to T. But now you are saying like we are trying to find out all those nodes, set of nodes for which the capacity would be more than the existing capacity C. So there might be a possibility that you are not able to reach the sink at the end, but you are trying to like find out
which ones I can reach.
Yeah.
Right. And if I could have reached the sink, what would have gone wrong in my reasoning? If I could have reached the sink, then that means there is a path from S to T where I can push more than C flow, because every edge has more than C capacity on it. But I just said that's not possible. I just said that the maximum was C. Right? So if I looked over my graph carefully and I found that the best flow I can push is C, and I then look at all the nodes I can reach with edges of capacity more than C, I cannot reach the sink, just by definition. So this is a cut set, which means it has a cut value. Which means I should be able to reason about this cut value with respect to the flow. What is the maximum cut value? What is the cut value this is going to have? See? There are many edges coming out of it.
Greater than or equal to C?
Sorry?
Greater than or equal to C?
Yes. In fact, its flow, its cut value could be as much as C times E. Well, it's less than equal to C times E. The cut value is less than C times E. Right? Because each edge coming out has capacity at most C. Because this is the set, this is the cut set. And there are at most E of them. Right? Okay. So what we're saying is that the cut value, so let's call this set A. The cut away is less than equal to C times E, where E is the number of edges in the graph. E is the set of edges in the graph. I don't know how many edges there are coming out. It could be just one edge coming out. Each edge coming out of this cut has capacity at most C, and there are at most E edges. So the cut value of this cut is at most C times E. Right? Okay, so where am I going with this? Patience a second. But what can I say about the maximum flow in the graph with respect to this cut value? What do I know about any cut and any flow? What did we say about cuts and flows? Any cut is always more than any flow. That's why the min cut is more than the max flow. In fact, they're equal, right? So if any cut is more than any flow, any cut is more than the max flow. But this is a cut. So I can also say if the max flow is F star, right? Because again, think of what we're saying. We're saying I have a cut, it has a cut value. By definition, the max flow has to be less than this cut value. So that's fine. On the other side, well, this cut has a value, it's at most C times E. So now we do the trick that we use all the time, we just remove the cut. So now we basically have proven that okay. But let's turn this around. This is not useful in its current form, but this also means that just by flipping the argument around. In other words, I have just shown to you that if I choose the path that has the largest possible flow that I can push along, any path from S to T in the graph, then this flow I push is a reasonable fraction of the maximum flow value. It's greater than or equal to the true flow divided by something. It's not arbitrarily small. It's not 1. Okay? It's a function of the true flow value.
Can you explain that once again?
Okay. So the inequality, of course, is just a reconversion of this inequality. But the meaning of this inequality is that I'm saying that the flow value I am now able to push through this path is some fraction of the total flow value. Now I want you to go back to your divide and conquer and your recurrences and your especially decimation. Remember when I said something like, if I can show that I can take away some fraction of the input at every step, that I can make good progress? That's the kind of argument we're making here. That we're saying we're taking away some fraction of the total flow value at every step. It's a very small fraction, admittedly. F over E is a very tiny fraction. But we are making progress that depends on the flow value. Because as a consequence of this, if I now push this much flow, right? So if I now say, okay, so if I now push this much flow through the graph, so now I say, okay, now I say push C units through. What is the new residual flow value I need? So the new flow value, let's call it F prime star, is equal to F star minus C. That's how much left work I have to do. But we know this is going to be less than or equal to F star times 1 minus. Just by arithmetic. And again, maybe you don't see where this is going in, but at least the arithmetic is straightforward. I've shown you an inequality on C and that gives you a constant F star. But think of this number as some kind of, it's not a constant fraction, but pretend if it were. Suppose that was actually F star times 1 minus 1 over 5, let's say. So the next step I only had 4/5 of F left. If I keep repeating this, what is going to happen? You know that in some logarithmic number of steps you'll be done. Right? There will be log of F. So let's try to make this argument precise. That after one step, we've done this much. Right? After k steps, if you apply this argument over and over again, since F prime star is now the new F, and it's like a compounding thing, so after k augmentations, right, the new F star, so we'll call it F prime star, is less than or equal to, let's call it k, is less than or equal to F star times 1 minus 1 over e to the k. Because at every step you multiply this factor. At every step you're saying, and remember, because of the genius of the residual graph, I can treat every iteration as a brand new argument and make the same argument I just made before. And remember that these are integer values. At some point, so when will this process stop?
Then F times k is equal to 0.
Sorry?
When there is no more flow.
Yeah, well, this process will stop. The best way to think about it is that when this number becomes, okay, so this will stop when this becomes 1. It's an exponential thing, so you have to say when it becomes 1. So let's say, so what we're going to say is now, this process will stop when we've done enough iterations that the right hand side of this expression becomes 1. Okay? It'll never become 0. If you use continuous math, it'll never become 0. But at some point, it'll become some constant. What you're saying is become some constant. At that point, it doesn't matter anymore. You can just run one iteration every step and it'll be fine, right? So think of it becoming some constant. So we'd like to say that, what is the value of k? So find the value of k such that f star times 1 minus 1 over e to the k is some constant. Not c. Sorry, I shouldn't say c. Here's my answer. Let's say 1. Okay. So how do I solve for this? I can now solve for k, right? I can say, okay, so let's say I want to solve for k. So I'm going to say, so I want 1 minus 1 over e to the k to be something like 1 over f. Okay. So there's a nice trick that you should remember, which is very useful in computer science, that roughly speaking, if you take some number which is large, let's say some big number m, and you raise it to the power of m, this is roughly e to the minus 1. E is Euler's constant. And in fact, in the limit as n goes to infinity, this is exactly what it is. But even if it's not going to infinity, it's basically that, up to some small error. So I can rewrite this expression then as saying that I'm going to rewrite the left hand side as 1 minus 1 over e. I want to use that trick, so I'm going to put that e up there. Okay. So then I have to divide by e as well to make sure I didn't change my expression. Right? Times k. Okay. roughly equal to f star to the minus 1. But this is basically, this is another way of writing this is basically as e to the minus k over e should be roughly f star to the minus 1. Okay? So then basically we now get, after solving this, that k should be roughly e. Why? Because you substitute e log f star, the e cancels, you get e to the minus log f. So what's going on here? There's a lot of analysis here, and again, as with most analysis, and this is what I said last time as well, try to find the deeper meaning. The deeper meaning here is saying that at every step I make a certain amount of progress, but the progress is controlled by the number. Once you prove that, you should know that you're going to get an answer like this. The details of how you prove it are this algebra here, and that you should go through. But there is a basic shortcut step that goes, once you have that, you are going to have this. The only question is what exactly it looks like. Yes?
If I have 1 minus 1 by 2,
Yeah.
then I will never go to 0.
That's why this works in the limit. And then if you think of E is usually a big number, right? The number is the graph. And we're doing asymptotic analysis. So there are ways to make these statements more precise, but they get extremely hideous then, and it's even more hideous than this. So I don't want to go there. But yes, these work in the limit. But we always reason asymptotically for large values of n. That's why these are approximately much better.
Okay.
So what this is saying, the most important bit, yes.
How did you get 1 minus 1 over e raised to the kth power? Because I'm getting 1 minus k over e.
No. If you remember, after one step, you've now scaled your flow. You've reduced your effective max flow by that much. That's a multiplicative. After the next step, you multiply again. Again, it's like a compounding thing.
Okay.
At every step, you take the current flow possible and you scale it down by that factor based on the reasoning we just outlined in the previous page.
Right.
So it always multiplies.
What I was thinking is you could say like your maximum flow is f star and you subtract initially that capacity from that first iteration c, and then on the next iteration you would subtract another capacity c prime.
Yes, you would.
It would be bounded below by f star over e.
But that won't be true for the second one. For the next one, you have to reason about the residual flow in the graph you just updated. So the problem is, for the first step, you can reason about the flow f star. For the second step, you have to reason about f prime star. And that becomes your f star, and that's what you multiply by. That's why you just keep multiplying over every step. You're not additively doing this, right? And that's a good point. If you were doing this additively, then yes, you're right. It would be 1 minus k over e. And in fact, if you squint very hard, the binomial approximation of this is in fact 1 minus k over e. Is that right? Yeah, if you do the Taylor expansion of this, that's the first term. So after a simple, but it's not a good enough approximation.
Okay, yeah, that makes sense. Yeah. So then why on the very bottom you have f star 1 minus 1 over e to the k is approximately equal to 1?
I want it to be true.
So I was thinking...
I desire this because I want to know when this process will stop. It has to stop somewhere.
Right.
It's only going to stop when I have a constant number of units of flow left. Because then at that point I don't care what Ford Fulkerson is.
Oh.
If I only have a constant amount of flow left in the graph, then I know Ford Fulkerson can do it. They can do constant number of stuff. That's okay. The problem is when the flow value is huge. So the idea is to use something clever to bring the flow value down to something really small. And then Ford Fulkerson is great, because if there are 2 units of flow, it'll do 2 iterations, it'll be done.
Okay.
So that's why it doesn't matter if it's exactly 1, it has to be some constant.
Some constant.
Yeah, but 1 is convenient just to make the argument.
Right. Okay.
And then once you do that, you just have to do this is just algebra. This is the only thing that looks mysterious, but it's not. This is a very common trick when you think about algorithm design. Again, it's the same as decimation, but with a bit more of a twist, because now I'm not removing a constant factor at every step. I'm removing a factor that depends on e. So it's quite small, in fact, but the argument remains the same. That this is why decimation works. That up to logarithmic number of iterations. Okay? Questions? So just to wrap up, before I can take more questions, what we have now shown is that if you take the fact pipe algorithm, after these many iterations, you are guaranteed to stop. And now, if you compare this to the original Ford Focuser, that would be, instead of this, you have C, which are F star, if you wish, the total capacity. Right? So this is a lot better. This is log of that. And that's what we need to get polynomial. Now our running time depends on the log of the numbers in the input. And that's why this is polynomial time versus that. This is still, by the way, expensive. I haven't yet told you how much time it's going to take to produce a single fat pipe path. You have to essentially run an MST-like algorithm to find this path. It's called a bottleneck MST. You find this path, it'll take you something like E log of V time. So the total running time of this algorithm is going to be, okay, so the total running time of this algorithm is now going to be, so you need to do, so you need an MST-like procedure to find the bottleneck path. And that would take, and again, you can look at the notes, it's something like, from MST-like time to do this, but a bit worse. And then you have to do K equal to iterations. So the total time of fat pipes is E squared log V log F star. And you compare this to basic FF, that was basically E times F star. So I'm not saying that this algorithm is always better than Ford Focuser. It's pretty easy to see that there are going to be many situations where Ford Focuser will do way better, especially if F star is small, because you're paying E squared versus E. But if F is very big, and in particular we know F can be exponential in the size of the input, then this is going to give you a better idea. Okay? So I'm not saying it's strictly better. I'm just saying it solves the problem of potentially worst case not being followed. There are at least a few groups, 1, 2, 3, I think 4 groups, if I'm not mistaken, who have a project paper relating to flows. There are 2 groups who are looking at sort of new max flow estimation algorithms. There's one group that's looking at Jim Orland's paper. You're not here right now. And there's one group that was looking at the Goldberg, Tarjan, and Bush label paper. Not here? You have a memory problem. I could have sworn there was.
I don't remember.
Okay. Okay, maybe there were, but there'll be some flow. So, hopefully some of this will give you some context from why people will be looking at. To this day, people are trying to improve the running time of max flow. This is by no means the end of the story. There's a lot more going on. Any questions? So while fat pipes gives you a polynomial time algorithm, it still depends on the actual flow value. It depends on the numbers in the input. And as we've seen, if you have things like irrational capacities and all, this could get a little bit annoying just to deal with. You don't want to deal with bit precision and stuff like that. It's just where I'm a discrete algorithms person. I like things that are discrete and combinatorial. So the question then that often comes up in algorithm design is, can you get an algorithm whose running time does not depend on actual values in the input? It depends on the structure of the graph and things like that, but it only depends on the size of the graph, the number of edges and the number of vertices. It does not depend on anything else. This is what is often called a strongly combinatorial algorithm, because it just doesn't. It's an aesthetic thing. It's like, can we design algorithms that don't have to look at the actual capacities and actual things? And so the next algorithm we're going to describe, I'll start getting through, will do exactly that. It will avoid any reference to F whatsoever. It will be independent of what the flow value is. And that's, appropriately enough, is called short clips. And again, remember we have this notion of goodness. How do I pick a particular augmenting path in forward focusing? And the notion of good for the fat pipes was pick the one that allows you to push the most flow. Good here will be okay? And when I say shortest, I don't mean anything fancy. Just count the number of edges. Find the shortest one. And here, of course, it should be a lot easier to see how you actually find such a path. Given a graph, a directed graph, can I find the shortest augmenting path from S to D? What do I do? Easy way to do it. Okay, nothing too complicated.
Breadth first search.
You can do a breadth first search. Right? Do a breadth first search, not a DFS, but a BFS, you will get the shortest path. So in time E, you can actually do this. So that's what we're going to be playing with. We're going to be playing with something that we know takes E time per iteration. And the only question is going to be, just as before, how many iterations you need. So it's the same argument as last time. We have a better way to describe good, and we want to hopefully use that to say the number of iterations required is going to be much less. So I'll just put a note here saying, so how do we reason about this? So we're not going to finish this argument today. It's a little bit more involved with some of the other arguments you've seen. So I'll start the argument today. And again, it's all in the notes. So we can, I'd encourage you to go and read the notes and we'll continue to finish the argument next time. But it's a kind of a clever argument. And in order to reason about this argument, we will define a notion of a level. So remember that what's happening is that we started with the graph G. Oops, sorry. So at some point we start off with the graph G, we call it G0. And then we do one augmentation that gets us to the graph G1. And we do another augmentation that gets us to the graph G2. And at some point we finish all the augmentations at some level G. And then we're done, right? The reason I'm saying this is because I want to talk about what happens at each, we'll call these stages there is in the graph. I want to talk about what happens at each stage. So now what I'm going to do is I'm going to define the notion of a level. So a level in stage I of a vertex V is the distance from S to V in Gi and is infinity if not reachable. Okay. So when you start off, all the vertices have, we can label them with how far they are from it. So you can do a VS from S and you can label every vertex for the first time you see it. Okay. So then you say, okay, it's level 1, level 2, level 3, and so on and so forth. So hopefully at the first stage, the level of T is not infinity. Otherwise, you can't even push any flow. So as we push flow, what is going to happen? What's going to happen essentially is that vertices are going to start looking like they're further and further away. If you remember the definition of the cut that I produced for Ford Fulkerson, I'm saying who are the people I can actually reach from S? At some point, some vertices are going to get so far away that the edges are going to go backwards, I can no longer reach them. And the distance will become infinity. And that will happen to T eventually. And once the distance to T becomes infinity, my algorithm is going to stop. Right? So GK is the first point at which the level of T becomes infinity. And once the level becomes infinity, can it ever go back to some finite value? If at some point in the graph, my distance to some node becomes infinity, will that ever change?
No.
Why not?
Some of the back edge, if it is not peaks, the back edge might fill, right?
If it's infinity, then the back edge might flip.
Because I have flow coming from the other direction.
So the argument here you're making is that I could reach it through some other path. But if I could reach it through some other path,
Then I wouldn't do these.
then it would be infinity again. So if you think of, you can think of how Ford Ferguson runs in many ways. This is another lens on the process. And this lens on the process says, instead of worrying about how much our capacity is going down at every step, whether it's going down by step by 1 unit, like in Ford Ferguson, or by lots as in fat pipes, let's look at how these vertices are getting pushed away from the source and try to analyze my algorithm based on that. Okay? And so we're going to show a couple of observations. And I think what I'll do is I'll give you the high-level observations and we'll reason about how they work next time. So basically what we're going to say is this, that first observation I'm going to make is that okay, so the levels always increase. That's what I just, they all, well, they never decrease. The level might stay the same in a particular stage, but it will never decrease. So once you hit infinity, you stay there. So that's the first observation we're going to make. So let's call this 1. And the next observation we'll make, and again, I'm not going to prove this right now. The next observation we're going to make, and I want to make sure I get this right. In some sense, as a corollary of the statement, so the second thing I'm going to say is that when you run this algorithm, so let's look at an edge, the directed edge from U to B. Okay. So what happens to this directed edge U as the algorithm runs? Initially, you push some flow through it, you keep pushing flow through it. At some point, it might disappear because it flips backwards. Right? It stays for a while, then suddenly it flips backwards. Then it might stay for a while backwards and it flips forward again. Then it might stay for a while forward and flip backward again. For any particular edge, this could happen because it depends on how you're pushing flow through it. So for example, if you remember our Ford Ferguson bad example with 2x, the 2x and the 1, that middle edge, its direction kept changing every iteration. First it was going down, then it was going up. Then it was going down, then it was going up. Then it was going down, then it was going up. Right? And that could happen to any edge. The key argument that we're going to have to make is that it flips direction at most V/2 times. And again, this is not going to be at all clear why this is true, so we'll have to prove that. But this observation is going to use the previous fact, the levels always increase. But why is this important? Because in every augmentation path, there is at least one edge that gets flipped. Why is that? Because you pick up augmentation path, you look at the smallest capacity edge around that path, and you push that much flow. What happens to that edge? It's saturated, right? You've chosen that edge because you could saturate it, so it's in the residual graph, it flips completely around. It doesn't have a bit going forward, bit going backwards. It has completely around. So if we are saying that in every step, something gets flipped, if we are also saying that no edge gets flipped more than so many times, how many iterations can you have? Well, for every edge, it can get flipped these many times. And every iteration, something gets flipped. So if you think of a budget of flipping, right? The total amount of flipping you can have is E times V/2. So again, so the total flipping possible is E times V/2. And in every iteration, you charge one of these things. You take away one of these from your bank of flips. So the total number of iterations. So that at least one flip per augmentation. Therefore, at most. Permutations, and therefore the algorithm now runs in time E times E times E over 2, which is basically E squared. No reference to flow at all. And again, if we now line up all the algorithms once again, we get basically the original FF was E times F. The next one was E squared log F star log V. And then we get this, which is this. So this running time is again worse than this one, depending on how bad F can be. This running time is worse than this one, depending on how F can be. But you get this prediction. Now we've completely eliminated any discussion. So this would work, assuming you could store the numbers properly, even if you had irrational numbers. It doesn't care. And actually, this will work as well, but this is. Next time, we will go into the argument as to why this works. It's actually very interesting. And the key idea, before you all back up, is that as you flip direction, your level increases. That's what you have to show. So if your level keeps increasing and you keep flipping as you flip direction, at some point it's going to become infinity. It becomes more than n if it becomes infinity. Because your level can never be more than n and still be some finite number, because there are only n nodes in the graph. That's the idea. And so we'll reason. Okay? Alright, we'll see you next week.